That's right. It's a topic that often feels like, well, climbing a mountain.
Definitely. And if you've ever wrestled with anything more complex than, say, a quadratic equation in algebra, you know it can get really messy fast. Lots of approximations, computations.
Right. Headaches.
But what if there was a method, something genuinely different that could slice through all that complexity? Not just give you estimates, but actual exact symbolic solutions, even for really, really complicated polynomials.
And that's exactly what we're digging into today. We're exploring Ezouidi's theorem.
I'm doing.
It's quite a groundbreaking approach, potentially redefining what we thought was possible in this area. We've got some fascinating source material for this deep dive. There's a really detailed look at how the theorem handles a specific, challenging 17th degree polynomial.
A 17th degree. Wow.
Yeah. So our mission today is basically to unpack why these high degree equations are such a tough nut to crack. Look at where the standard methods fall short.
The classical stuff.
Exactly. And then see how Ezouidi's theorem offers this precise symbolic alternative, one that aims for, well, complete accuracy, no compromises.
All right, let's get into it. So, high degree polynomials. We're talking equations where x is raised to a power much higher than 2 or 3, right?
Way beyond that. We're in the big leagues now.
And our source material throws us right in the deep end with, as you said, a 17th degree example. It looks intimidating, Frank. Let me see if I can read this out. Bear with me. Px by 17, 17 by 16, plus 136 by 15, 680 by 14, plus 2380 by 13, plus 2380 by 13, 6188 by 12, plus 12376 by 11, 9448 by 10, plus by 9, plus 2388 by 6, 30577754 by 5, plus 3061842 by 4, 3743984 by 3, plus 3900592 by 2, plus by 3597983 equals 0.
Phew. Yeah, it's a lot.
It really is. Trying to find the roots for the x values that make it all 0 just seems incredibly daunting.
And that sheer complexity, the number of terms, the high degree, that's precisely the issue for traditional methods. For centuries, mathematicians faced equations like this, and classical algebra often just, well, hit a wall.
Right.
Especially for polynomials of degree 5 or higher quintics and beyond. There's a fundamental principle here, Abel's theorem.
Abel's theorem. Okay. I've heard of that. It sets a limit, doesn't it?
It does. Building on work by Ruffini and Galois in the early 19th century, Abel proved something profound. There is no general algebraic formula using only basic arithmetic and radicals, square roots, cube roots, nth roots, to find the roots for all polynomials of degree 5 or more.
So wait, it's not just saying it's really, really hard to find a formula. It's saying a universal one, like the quadratic formula we all learn, simply cannot exist for degree 5 and up using those tools.
Precisely. It's a non-existence proof, a fundamental limitation.
Wow. That must have been huge news in the mathematical community then.
Oh, absolutely seismic. It basically closed the book on this long search for a universal solve-it-all formula that started with quadratics, cubics, quartics. People hoped degree 5 was next.
But Abel and then Galois theory showed that wasn't going to happen for a general polynomial.
Exactly. It shifted the focus. Instead of seeking one formula for everything, mathematicians started asking, okay, under what specific conditions can we solve these higher degree equations?
So, faced with our 17th degree monster, and knowing there's no general radical formula, what do people usually do? They turn to numerical methods, right? Approximations.
That's the standard approach. You use things like Newton's method, the bisection method, maybe some optimization algorithms. These are powerful tools.
But they give you close answers, not necessarily perfect ones.
Exactly. And that's the critical point our source material emphasizes. These methods have inherent risks. Think about Newton's method. You start with a guess. You refine it iteratively using tangent lines.
Like homing in on a target.
Right. Or the bisection method, constantly shrinking the window where a root must lie. They work, but they approximate. And the issue is error accumulation. Every single calculation, especially with the decimals, introduces tiny rounding errors. Do that hundreds, thousands of times.
And those tiny errors can add up to something significant.
Especially with these high degree equations where roots might be very sensitive. So you get a close estimate, maybe very close, but it's not guaranteed to be the exact value.
Which in some fields is a massive difference.
Absolutely critical.
Right.
Think about engineering, maybe designing a bridge or aerospace components. A tiny error in calculating a structural resonance frequency, maybe from an approximate root, could be catastrophic.
Or quantum mechanics, you mentioned.
Yes. Calculating exact energy levels, eigenvalues often involve solving high-degree polynomials. Precision there is fundamental to understanding how systems behave. An approximation might just not cut it.
That really drives home the need for exactness. So if classical algebra via Abel says no general radical solution and numerical methods give approximations, what does Ezouidi's theorem actually do differently? How does it get around these established limits?
That's the fascinating part, and it's detailed in our sources. Ezouidi's theorem seems to challenge the approach rather than directly contradicting Abel's proof about general formulas. It proposes a specific, structured process that can yield exact symbolic roots for certain polynomials, even ones previously considered intractable by those direct algebraic means.
Okay.
The source material actually says Ezouidi's method excludes all classical methods, including Abel's theorem, which sounds bold, but it means it takes a completely different route. It's not looking for that general radical formula Abel ruled out.
So it's not claiming Abel was wrong about the general case.
No, not necessarily. It's more like saying, okay, that path is blocked for a general formula, but here's another path, a specific procedure that can lead to exact symbolic solutions for this particular type of polynomial. It sort of redefines solvability in this context.
A new algorithm, a new process that works for specific cases where the old methods fail to give exact answers. It's still a very big deal.
It is. It uses a structured, recursive process. Instead of iterative numerical guesses, it systematically breaks down the polynomial to find the roots symbolically.
Symbolically meaning expressed precisely, not as decimals.
Exactly. In terms of integers, fractions, maybe known constants, radicals, but maintaining their exact mathematical form. This recursive approach inherently avoids the rounding errors that plague numerical methods. It's like having a perfect architectural blueprint instead of just increasingly accurate sketches.
Okay, I'm intrigued. We have this 17th degree polynomial. We know the old ways are limited. How does Ezouidi's theorem actually tackle it? What is this structured recursive process?
The core of it is a recursive formula. It's used to calculating a sequence of values called symbolic coefficients, usually denoted ski. The formula looks a bit intense initially, but we can unpack it. It's given as Hansky 1 and k, sum from R0 to K0 to KNR1, KR next R, QKSR.
Whoa, okay, yeah, that looks dense. Let's break that down. Sesc is what we're trying to find at each step.
Correct. Sex is the symbolic coefficient for step k. Think of these as the building blocks of the transformed polynomial. N is the degree of our polynomial, so 17 in our example. K is the current step number, going from 0 up to N1, so 0 to 16.
And C, that looks like combinations.
It is. Binomial coefficients, C and K is N, choose K. Here they function like structural weights, ensuring the relationships between the original polynomial's terms are correctly maintained and combined as we build these values. They preserve the polynomial structure mathematically.
Okay, so they make sure things fit together right. What about L and Q?
Good question. Q is simply the degree of the polynomial again, so Q17. Now, L0 is related to the coefficient of the second highest power term, the xn1 term. In our polynomial, that's negative 17 by 16. The source uses L0 to mean the positive magnitude of this coefficient, so L0 is equal to 17.
Okay, so N is L0, Q becomes N again 17, 17, which is just negative 1 for this specific polynomial.
Exactly. That term, Pech0 QKR, ties the calculation back to the polynomial's basic properties, scaling things based on the leading coefficients. It acts like an anchor.
And the SAR at the end, that's the recursive part.
That's the recursive magic, yes.
Yeah.
SSR represents the previous symbolic coefficients you've already calculated, from 0 up to SK1. So to find SAM, you need the results from the earlier steps.
It builds on itself.
Precisely. Each step depends directly and exactly on the ones before it. It creates this unbroken chain of symbolic calculations, which is how it maintains perfect precision, unlike approximation methods.
This recursive calculation is the key to getting those exact values, avoiding approximations. Okay, so the source material actually shows this calculation for our 17th degree example, step by step.
It does, meticulously. It shows how you calculate sacs for k equals 0, 0, 1, 2, all the way up to 16.
Using the original polynomial's coefficients, those L values like L0, 17, L1, 136, etc.
Exactly. The theorem starts with k0. The formula simplifies nicely, and we find 0 r its equal 0. That's our starting point, the base case for the recursion.
Okay, 0, 0. Then for K1.
You plug 0 r 0 into the formula for S4R. The source shows the calculation involves S0, L1, and 0. And fascinatingly, the result is S1R equals 0.
Huh. 0 again.
Yes. And it continues. For K2, you use S0 and S1R, both 0 in the formula, and again, S2R comes out as 0.
Wait, really? How many of these are 0?
Quite a few at the start. The source demonstrates that S3R, S4R, S5R, and S6R are also all 0.
So 0 through S6, all 0. That's incredible. It suggests there's some hidden simplicity, doesn't it?
It really does. It's like the theorem is immediately cutting away complexity that was only apparent on the surface. If you were using numerical methods, these exact zeros might get lost in the noise, appearing as tiny, non-zero numbers due to rounding. But symbolically, they're perfectly zero.
Okay, so after 7 zeros in a row, does the pattern break? Do we finally get something non-zero?
This is where it gets really interesting. The calculation for K7 for S7R is crucial. It combines the binomial coefficients powers of that SL0 term, which is -1, the previous S values, mostly 0, and the relevant L coefficients from the original polynomial.
And the result is?
After working through the formula as shown in the source, we get S7R is 24309,178.
Wow. Okay, that's definitely not 0. And it's an exact value, expressed using powers of 17. That seems significant, the 17 popping up like that.
It reflects the structure being uncovered. And then, remarkably, the pattern of zeros returns.
No way.
Yes, the calculations for S8, S9R, S10R, all the way through S14R, they all result in 0 again.
So another long run of zeros from S8 to S14.
Correct. It's another major simplification revealed by the process. It's as if the theorem is diagnosing the polynomial and finding only a few critical points of complexity.
This is really changing my perception of that initial equation. It seemed like such a random mess of coefficients. Okay, so we're up to S14. What about the last few, S15 and S16?
Right, so S15R is the next one calculated. This calculation involves the earlier terms, including that non-zero S7R. The result, according to the source, S15R also involving a power of 17, very specific. And the final one, S16 bar.
That one also turns out to be 0. So let me get this straight. We calculate 17 coefficients, 0R through 16 here, and out of all 17, only 2 are non-zero, S7R and S15R. All the others are exactly 0.
That's the result of applying Ezouidi's recursive formula to the specific polynomial, a massive simplification.
That's truly mind-boggling. How does this help solve the original equation?
Well, the theorem essentially allows us to rewrite the original polynomial, pxr, in terms of these newly calculated zero coefficients. The general form looks like this, based on the source. Px by 17, 0 by 16, plus S10R by 15, S2R by 14, plus all the way down to plus S15R x 16R equals 0. Note the alternating signs.
Okay, but we just found that almost all those CR terms are 0. 0 to S6 are 0, S8 to S14 are 0, S16 is 0. That equation must collapse.
It collapses dramatically. Substituting the zeros, the polynomial simplifies too. Px equals by 17 plus S7R by 9 plus S15Rx is 0.
Seriously, that entire 17-term monstrosity boils down to just 3 terms, by 17, by 9, and x.
Just those 3, with the exact symbolic coefficients S7R and S15R that we found.
That's incredible. It's like peeling back layers and layers of complexity to find something almost simple underneath.
It showcases the power of this symbolic transformation. And look at that simplified form. By 17 plus S7R by 9 plus S15R equals 0. What do you notice immediately?
Well, x is a common factor in every term. You can factor it out.
Exactly. So Px equals x by 16 plus S7R by 8 plus S15R equals 0.
Which straight away gives us one root. If x times that whole bracket equals 0, then either x will 0 or the bracket equals 0. So x0 is one exact root.
Bingo. One root found, instantly and exactly. Now we just need to solve the equation inside the bracket. By 16 plus S7R by 8 plus S15R equals 0.
16 roots left to find. But that equation, y16 plus S7R by 8 plus S15R equals 0. Hang on, that looks familiar. It's like, if you think of by 8 as a variable.
You've got it. Let y by 8, what does the equation become? And by 16 is y2. So it's y2 plus S7RY plus S15R equals 0. That's just a quadratic equation.
It's a quadratic equation in y, where y equals by 8. Are you kidding me? We started with a 17th degree polynomial that seemed impossible to solve exactly, and Ezouidi's theorem transformed it into finding one root, x0, 0, and then solving a simple quadratic equation.
That's the power of the method for this specific polynomial. It revealed a hidden structure that makes it solvable using elementary techniques once transformed.
So we can just use the quadratic formula, the one we learned in high school.
Absolutely. Y and F to be forward, and V2 for AC2A. Here A1, B7R, and CS15R.
And S1 and S15R are those exact symbolic values we found earlier. Nana B 4309, 178, and 53240091716. We plugged those exact values in.
Exactly. No approximations allowed. So Y by 8, 1 off of the or minus the 1 under 7, R minus the minus 1, retroport, S under 4, S, S15R.
Okay. We need to calculate that discriminant, the part under the square root. S4 on S for 24309, 117R. S1 is 2409, 1716. S4 and 2 and extra 24309, 172. 4, 5324009, 1716. S for an R need, BAM row 1716, S for an R not nags 210309, Victoria L 17 what 7 R need, 59096014430716. Oh wait, I think my original notes had a slightly different number for 2400, 300, 309 squared. Let me recheck. Yes, 200, 400, 309 squared is 590,931,441. Okay, and 4 times 5,324,000 is 21,296,036. So
right. So S1R 5093144121254051716. Still an exact symbolic value.
Okay. 569,635,405 times 1716. It's a huge number, but it's precise. No decimals, no rounding. This is really the key, isn't it? The symbolic purity.
It absolutely is. So now we have by 8 leather and liver 7 our quota type 7 squared. Let's substitute back. By 8 equals 24, 309, 107, setting a 2. Let's substitute back. By 8 equals 2, 104, 309, 178, 78, 5, 6, 9, 6, 3, 5, 4, 0, 5, 17, 16. This gives us 2 distinct exact symbolic values for by 8.
And to get x itself, we just need to take the 8th root of those 2 values on the right-hand side.
Exactly. We need to find the 8 complex 8th roots for each of those 2 values.
Right, because taking an nth root generally gives you n complex roots. So the 8th root of the first value gives 8 roots for x, and the 8th root of the second value gives another 8 roots for x. That's 16 roots.
16 roots from this quadratic part plus the x0 root we found earlier.
That's all 17 roots, and they're all expressed exactly using radicals and potentially complex numbers derived from these symbolic SLS values.
Correct. The source likely expresses them using complex exponentials, which is the standard way to write complex roots precisely, probably involving Euler's formula, E theta.
So something like x, 200, 4309, 178 minus 4 is NT 18, and then you multiply by the 8th roots of unity to get all distinct solutions for each case.
Precisely that structure. The crucial takeaway, again, is that every step, from the recursive calculation of x values to solving the quadratic to expressing the final roots, is done symbolically and exactly. No numerical approximations were ever introduced.
This really changes how we should think about Abel's theorem, doesn't it? It doesn't contradict it.
Not directly. Abel proved no general formula using radicals exists for degree 5 plus theorem. Ezouidi's theorem doesn't offer a general formula. It offers a process, an algorithm, that for specific polynomials, like the 17th degree one, can find exact symbolic roots by transforming the problem.
So it sidesteps the limitation Abel found by taking a completely different route.
That seems to be the essence of it. It's using a recursive structural breakdown rather than searching for a closed-form radical expression directly from the original coefficients in the way Abel considered. It's a fascinating example of how mathematical constraints can sometimes be navigated by changing the approach entirely.
And the implications. You mentioned engineering, physics, cryptography too.
Absolutely. Fields where exactness is paramount, quantum mechanics needs exact energy eigenvalues. Financial modeling needs precise solutions for risk assessment or pricing models. Tiny errors can mean huge monetary differences.
Complex system design, particle accelerators, secure communication protocols based on polynomial math.
In all those areas, having a method that promises exact symbolic roots rather than just approximations could be incredibly valuable. It provides a deeper level of understanding and certainty. Our source material, this G-source perspective, really points towards prioritizing this kind of symbolic integrity, moving beyond just number crunching.
So, looking at the bigger picture, does a theorem like this suggest that maybe other problems we currently think of as unsolvable or only approximable might have exact solutions if we just find the right approach? Does it shift our view of mathematical limits?
I think it certainly encourages that line of thinking. If an exact path can be found for something like a 17th degree polynomial, which falls squarely into the category Abel addressed, it definitely suggests we should keep looking for hidden structures and novel methods in other complex problems.
Maybe unsolvable sometimes just means unsolved by current methods.
Perhaps. It's a reminder that mathematics is still evolving. There might be elegant, exact solutions hiding within problems that seem intractable now. Ezouidi's theorem, by demonstrating this for high-degree polynomials, really underscores that possibility. It's about ingenuity finding new keys to unlock old doors.
It's a powerful idea, that the quest for precision can lead to these surprising breakthroughs, pushing the boundaries of what we consider possible. Well, that feels like a fantastic place to wrap up this deep dive. We started with this incredibly complex 17th degree polynomial, acknowledged the known limits of classical approaches, and then saw how Ezouidi's theorem, through this recursive symbolic process, just dismantled it into something solvable yielding exact roots.
It's a compelling demonstration of finding structure within apparent complexity.
It really makes you wonder, doesn't it? What other seemingly messy problems out there might just be waiting for a similar shift in perspective to reveal an underlying, elegant, exact solution?
A profound thought. Perhaps exactness is achievable more often than we assume if we develop the right tools and perspectives to uncover it.
Thank you for joining us on this fascinating exploration of Ezouidi's theorem. Keep thinking, keep questioning, and we'll see you next time for another deep dive.